Okay, guys, welcome back. So, last time we talked about the positions in the sky, how to find things in the sky. We talked about how the altitude is the distance above the horizon, the azimuth is the distance around the horizon. And if I have those two coordinates, I can go over to azimuth and up a certain altitude and I can find anything in the sky. But we also talked about how there are two things I need to know in order to use this coordinate system. I need to know the time, which of course includes the date. And then I also need to know my position on the Earth. So, the fact is that a star's altitude and azimuth are changing all the time, and there's nothing I can do about that. So it's not going to be terribly useful for star maps, which is what we're going to talk about in the next lesson. So in this lesson, what I want to talk about is what's causing those changes. And there are three motions of the Earth that are causing these changes over the time. And so there's the rotation of the Earth, the revolution of the Earth, and what's called the precession of the Earth. And we'll go into each of these individually. But what I want you to get out of the video is what each of these motions are, how long they take. So you've got an idea of the time scales for them, days, hours, weeks, months, whatever. And then what primary effect they have on the sky. So what effect do they have? What are they causing when we see that? All right, let's get started. Okay, so this is the same diagram that we had when we were talking about positions last time. You see that we're pointing towards Polaris here, so we're looking at the side of his head right here. And then we had this star that rises in the east, starts over here, and then reaches a maximum in the south, and then it'll start to come back down and it'll set in the west. So try to visualize that as one star moving through here. And so at 9 o'clock, then we decided that its altitude might be, well, I don't know, maybe 30 degrees or so, and its azimuth might be about 105, 110, somewhere in there. Then at 11 o'clock, now it's directly above the southern horizon. So its azimuth has changed. It's at 180, and now it's up at its maximum altitude, maybe 60 degrees. So the altitude and azimuth are obviously changing. So the question is, why? Why does the star appear to move? Well, it's because the Earth is rotating. And so what's happening is we're rotating towards that 90-degree mark there. So as we move towards 90 degrees, the star doesn't move, but it seems to get higher and higher up in the sky like that. So the altitude and azimuth then are changing over time, and that's the evidence of the first of the three motions that we're going to be talking about. So rotation is the first motion, and that rotation is always one body spinning on its axis. So we're always talking about one body that's just turning on its axis like that. So what you've got here, this is called a star trail picture. And so what they did was they had a camera sitting on a tripod and they just pointed it at Polaris, pointed it at the North Star, and left the shutter open for several hours. And then the Earth rotated, which made the stars seem to rotate. And right here, you can see that there's one star there that's not smeared. That's Polaris. It's actually pointed towards it. And so all the rest of the stars, though, are smeared. And this is the only way that we can actually measure the rotation of the Earth. We can say, okay, so let's say I took this picture for an hour and the star moved this many degrees. Well, then how many hours would it take to go 360 degrees? And so from that, we can measure the rotation of the Earth. And it turns out it is not 24 hours. The length of the day is actually not 24 hours. That's a myth. It's 23 hours and 56 minutes. So it's just slightly shorter than 24 hours. Now you may say, well, okay, so is our 24-hour day just kind of an approximation? Well, no, it's not. And we'll talk about what the difference is there in just a minute. But when we look at this diagram here, so here we're facing north, the same view that we see here. So Polaris is right there in the middle. And you see that star appears to rotate as it comes around. These stars that are right next to the pole here, right next to the pole star, they never set. You can see that all of these stars are going to be visible all the time. So even during the daytime, Polaris is visible even in the middle of the day. You can't see it because the sun's shining, but it's actually there. So these stars are called circumpolar stars. And circumpolar means around the pole. So those are stars that are very close to the pole. They're circumpolar. Other stars, as we get farther away, they seem to rise in the east, they reach a maximum in the south, and then they set in the west. Okay. So the second motion is revolution. Now, this is not power to the people or anything like that. This is one body going around another, and that's one way that you can tell the difference. Revolution is always about two bodies. Rotation is always about just one. So the Earth does not rotate around the sun, it revolves around the sun. The moon rotates on its own axis and then revolves around the Earth in the same way. And so revolution then is Earth orbiting the sun. Now you see that our planet is tilted. We've talked about this before, how our axis happens to be pointed towards Polaris here. So that's why Polaris is our North Star. So one of the results that we see of the fact that we're in different positions in the orbit and because we're tilted is that we have seasons. Now, I'm not going to embarrass you by having you, post email on what you think causes the seasons, but I want you to pause the video and say to yourself, actually write it down. Why is it warmer in the summertime than it is in the wintertime? What is your explanation for that? Nobody is ever going to see it except you. But I want you to pause the video and answer the question, why is it warmer on Earth in the summertime than it is in the wintertime? Pause the video, write that out right quick, and then come back. Did you actually do it? Because this is actually one of the biggest myths that's out there. There was actually a video that was made. They interviewed a bunch of Harvard graduates on the day of their graduation, and they asked them the very same question that I just asked you. Why is it warmer in the summertime than it is in the wintertime? And almost all of them got it wrong. So by the time you finish this class, you are going to be smarter than a Harvard graduate. So how many of you thought that you wrote down, well, it's warmer in the summer because we're closer to the sun? Yeah, not so much. We are actually very slightly closer to the sun in January. We're actually, our perihelion, our closest approach to the sun is in January. We're actually farthest from the sun 6 months later from that. So obviously for us, January is not summertime, so that's not what's causing it. And if you think about it, that actually kind of makes sense because you probably knew that the northern and the southern hemispheres have opposite seasons. If it was because of how close we are to the sun, well, then we should all have the same seasons all over the planet, right? So you know that that can't be it. Well, some people go take it just a little bit more sophisticated, a little bit farther, and they say, well, then no, it has something to do with the tilt. So maybe it's because when we're tilted towards the sun, we're closer. Well, no, not really, because this diagram here is not drawn to scale. If I were to draw this to scale with the sun this size and this distance, Earth would be less than the smallest dot that I could draw on this page. It would be tiny, tiny, tiny. And there's just no difference from even one side of the planet to the other side of the planet, much less just from some tilt. You're effectively the same distance from the sun all the time. So it's not that we're closer when we're tilted. That is also not what's causing the seasons. So you may say, okay, so what is causing the seasons? Well, the key here is direct and indirect sunlight. So if you look here in the northern hemisphere during the summertime, the sun, all the sun's rays are concentrated in a very small area right here. So that small area, all that energy is in a small area, and so the ground gets hotter, which makes the Earth warmer in that particular area, and so we're going to have warmer sky, warmer days. On the other hand, in the southern hemisphere, that same energy gets spread out over a much larger area. Can you visualize that? I'm going to try to draw that with my pen here. So here, it's all going to be concentrated, whereas here, it's going to get spread out. And so instead of having all the energy concentrated in that one little area, it's spread out over a much larger area. That means each part of the Earth gets less energy, and so it's going to be colder. So this is why it's warmer in the summer, because we've got direct concentrated sunlight. And then in the wintertime, it's spread out. Now, you may have also thought, well, we have longer days in the summer, and that actually has an effect, but it's a small effect. So, if, for example, if this is the effect due to the concentrated sunlight, then that's the effect due to having longer days. It's real, it's measurable, but it's not really that important compared to the amount of direct sunlight. And if you think about it, the North Pole has 24 hours of daylight and 24 hours of nighttime. So if the length of the day mattered, then the North Pole should be the hottest place on Earth, shouldn't it? But it's obviously not. Well, the reason the poles are always cold is because no matter what the season, that energy is still being spread out. Do you see that even up here at the North Pole, it's getting spread out a lot more? So that means that it's going to be cold no matter what the season. On the other hand, at the equator and in the tropics, you're almost always getting pretty close to direct sunlight all year round. And this is why it's always warm in the tropics. So it's that direct sunlight that's making the difference. All right, so now that we know what causes winter and summer, what's happening is the Earth, remember, let's say that this is the sun. The Earth is keeping its pole pointed towards Polaris all the time. So if Polaris is this way on my particular screen, on yours it's going to be, opposite. But I'll try to do my hands the way yours is. Don't know if I can do that. Okay, so let's say that I'm pointed towards Polaris. When I'm on this side of the planet, when I'm on this side of the sun, I'm going to be pointed towards Polaris, and the southern hemisphere is going to get direct sunlight, whereas the northern hemisphere is going to get indirect sunlight. So it's summer in the south and winter in the north. But when the Earth revolves around the sun, it keeps that angle pointed towards Polaris. But now it's positioned like you see here, where the northern hemisphere is getting that direct rays. So the angle, the pole is always pointed towards Polaris as we go around. So summer and winter correspond to positions in our orbit. The axis of the Earth doesn't go back and forth. It's where we are in our orbit. So on this side, during the winter time, we're pointed on this side of the sun. And so I can see the constellations on this side of the sun are Taurus, Gemini, and Cancer, and a couple others. But these then we would call wintertime constellations. Wintertime. Why wintertime? Well, it's winter for the northern hemisphere, and that's what they're named for. And do you see that I can see these because in order to see it, I have to be dark. So I need to be on this side of the planet from them. Now, over here, at night, I can see these constellations. During the day, Taurus, Gemini, and Cancer are still up, but now the sun's shining, so I can't see them. So the only ones I can see over here are Scorpio, Ophiuchus, Sagittarius, and Capricorn. So these then we consider to be summertime constellations. Now you may say, wait a minute, Kilo, I'm a Gemini and I was born in May. Well, okay, true. May is closer to summertime than it is to winter. But remember, here's how astrology works. Astrology, your birth sign, is based on where the sun appeared when you were born. So if you think about it here, if this is Gemini, when you were born, if you're a Gemini, then the sun was in the constellation Gemini. So Gemini was behind the sun. Well, obviously, you couldn't actually see Gemini because the sun was shining from that. So that's where the summertime and the wintertime constellations come from. So it turns out, though, there are actually 13 constellations to the zodiac. So if you were born in the wintertime, there is a reasonable chance that you are actually an Ophiuchus, the snake bearer. So good luck finding your horoscope in the newspaper for that one. All right, but that's what's determining your zodiac sign, is what position was the sun in. All right. Now, we talked about how the rotation of the Earth is 23 hours and 56 minutes, but our day, what most people think of when they talk about a day, is actually 24 hours. It's not an approximation. It's exactly 24 hours. We define the solar day, which is what most people mean when they say day, as being the time from noon to noon. So the time from when the sun is directly overhead until the sun is directly overhead again. And that is, in fact, exactly 24 hours. So look at this diagram and you can kind of see what's going on here. So if the Earth were not rotating, then I would stay right here. 23 hours and 56 minutes later, the sun would be back over my head. And so my solar day would also be 23 hours and 56 minutes. But the Earth is also revolving around the sun. So after 23 hours and 56 minutes, I've gone 360 degrees, but the sun isn't directly over my head. And so I need to turn just a little bit more, 4 minutes more, before the sun is directly over my head. And this is why the solar day is 4 minutes longer than the sidereal day. But, the thing is, guys, that the solar day is really just an illusion. It's based on where you are, the fact that you're standing on the surface of the planet. The sidereal day is real. So in this class, when we're talking about rotations and how long it takes something to go around or how long it takes it to spin, we're talking about the sidereal time because that's what's real. I mean, here's one I want you to think about. Here's a little puzzle for you. Suppose the rotation period of the Earth was not changed. So 23 hours and 56 minutes. Sidereal day is the same. Now, let's suppose that the Earth is going around the sun twice as fast. So its revolution period is now only 6 months because it's going twice as fast. So my question to you is this: would the solar day get longer, shorter, or stay the same? Pause the video, make yourself a diagram, work it out, and then come back and let's talk about it. Okay, so the question was, if the sidereal rotation, the sidereal day stays the same, 23 hours and 56 minutes, but the revolution period is twice as fast, what happens to the solar day? Well, if you think about it, I'm right here. 23 hours and 56 minutes later, I'm still going to be pointed straight ahead, but now I'm going to be all the way up here. Let's see if I can draw that. Yeah. Do you see that I've got to turn even further in order to get so that the sun is directly over my head? In fact, I'm going to have to be all the way over here before the sun's over my head. So that means then that the solar day is actually going to get longer. Think about it. This is one of those tricky ones that's really kind of hard to visualize. When I do this in a live class, about one third will say longer, and one third will say shorter, and one third will say it stays the same. But see if you can figure out why the solar day had to get longer. Pause the video here and go through that logic and see if you understand it. Okay, so it still takes me 23 hours and 56 minutes to go 360 degrees, but now I'm way up here, so I've got to turn even farther, and that's going to make the solar day longer. All right, so there's one other motion, that's precession. Now, this is not one that you can generally sense in your lifetime because it takes 26,000 years for the Earth to precess once on its axis. So precession is a wobble. If you've ever played with a top, you know how that top will eventually start kind of wobbling like this, or you can take a quarter and spin it, and then that quarter will eventually start wobbling. That's precession. Well, Earth is just a top spinning on its axis here, so it's precessing. Right now, we're very close to being pointed towards Polaris. When I'm a great grandfather in about 13,000 years, we'll be pointed towards Vega. And so Vega will be our North Star. Do you see how that is? So we go around this way, 13,000 years, I get to Vega. Another 13,000 years, I'll get over to Polaris. And in between that time, there really aren't that many bright stars. And so for most of the time, we won't have a North Star. It's purely a coincidence that Polaris is our North Star right now. So the right now, even we're already about half a degree off from Polaris. So let's do an experiment here. Get my picture to show here. There we go. So this is printed at the bottom of page 2. I want you to pause the video and I want you to think about it. So now, whereas before we were pointed towards Polaris this way, now we're pointed towards Vega in this direction. So first of all, I want you to figure out, is this a wintertime constellation, or is it winter for the Northern Hemisphere, or is it summer? Pause the video, think about it, and let's put that right there. All right, so we are tilted towards the sun, which means we're getting concentrated sunlight in the Northern Hemisphere. Is that summer or is that winter? That's going to be summer. So now, whereas used to be our summertime position for the Northern Hemisphere was over here, now our summertime position is all the way over here. So if it's summertime here, these guys are getting indirect sunlight. What season is it for the Southern Hemisphere? That's going to be wintertime for them. All right, 6 months later, we've moved in our orbit so that we're on this side of the sun. We're still pointed towards Vega, just like always. So now what season is it for the Northern Hemisphere? Pause the video, work it out. Okay, so we're getting indirect sunlight here. So that's going to be winter. The Southern Hemisphere, on the other hand, is getting that direct sunlight. So that's summertime for them. So now this is our summertime position, and this is our wintertime position, which is the opposite from what it was over here. Okay, so the last thing then, the constellations, though, haven't moved. Scorpio, Ophiuchus, Sagittarius, Capricorn, Taurus, Gemini, and Cancer. They're still on this side. They haven't moved. But now I can still see these when I'm on this side of the sun, right? But that's now summertime for me. So whereas these used to be wintertime constellations, 13,000 years from now, these will be visible in the summertime. Same thing over here. These are still visible when I'm in the same part of my orbit, but now this is the wintertime position for me. So these now become wintertime constellations. So the Earth will very slowly precess like that And that's changing which constellations are going to be visible during which seasons. It's also why astrology needs to be updated. You're probably not the astrological sign that you think you are. Because you think about it, there are 13 constellations. It takes 26,000 years to go around. So about every 2,000 years, we will have precessed by one constellation of the zodiac as we go around. So, for example, I'm a Gemini. Okay, now, first of all, I don't really believe in astrology, but I'm a Gemini, and Geminis are naturally skeptical. So, But theoretically, the sun was in Gemini when I was born at the end of May. In reality, it wasn't. The sun was actually in Taurus. So I'm really a Taurus, not a Gemini. 2,000 years ago, I would have been a Gemini, but because I was born in this century, that means that I'm actually a Taurus. So before you get a tattoo, go figure out what your actual birth sign is. And what I suggest you do is look in the resources, and there's a link to Stellarium, or you can go to stellarium.org, download the program. It runs on a PC, it runs on a Mac, it even runs on your phone. And set in your birthday. Then find the sun and see which constellation is behind the sun. That is your actual birth sign. All right. Okay, so in summary, then, we've got three motions of the Earth. Rotation is the Earth spinning on its axis, and it takes 23 hours and 56 minutes. And the major thing this is what's causing things to rise and set. So if you're seeing something change over the course of a day, that is probably due to Earth's rotation. All right, so the sun rising and setting, the stars rising and setting, that happens over the course of a day. You can see it happening. So that's because of Earth's rotation. Revolution, on the other hand, is Earth orbiting the sun, and that takes 365.25 days. So let me pause here, though. You see that 0.25? This is what's causing your leap year. We only have 365 days in the year, so that means each year we're getting a little bit off from where we should be. After 4 years, we're a full day off. So we add in an extra day in February, and that's why we have 366 days during a leap year, because we're just carrying forward that extra 0.25 days each time. So this is what's going to cause our wintertime and our summertime constellations. It's not causing the seasons. The seasons are caused by that direct sunlight, but where we are in our orbit determines whether we're getting direct or indirect sunlight from that. This is also why we have a 24-hour solar day instead of a 23-hour and 56-minute day, because by the time we've turned 360 degrees, we've moved a little bit around the sun, and so I've got to turn a little bit more to get pointed towards the sun. Precession, that's the third motion. This one takes a lot longer. So revolution, anything that's happening over the course of several months, that's going to be caused by revolution. Precession takes 26,000 years. So now you're talking about changes that happen over thousands of years. So we'll have a different North Star. Which constellations are north or summertime and wintertime will change. And then, of course, your zodiac signs are changing as well. All right, so that's it for this one. Go ahead and download the motions practice sheet. Go ahead and work that out. I strongly recommend that you come into Live Help and let's go over it. And let's see what let's compare your answers, take 5-10 minutes, and then we can actually make sure that you're on the right track. These will be graded as accuracy for always. Okay, so you can also use how things rotate in the sky to kind of access your inner Crocodile Dundee, right? You're going to see that when you're working on your practice today. But because it takes 24 hours for the stars to rotate one time around, you can find something recognizable like the Big Dipper, the 4 stars of the bowl and the 3 stars that come out on the handle. And if the Big Dipper is oriented this way, you know that 12 hours later it'll be this way. So if you go outside and let's say it's 11 o'clock or so, and you see that the Big Dipper is oriented like this, and you go out partying with your friends and you kind of stumble out of the club or whatever, and you see that the Big Dipper is over here. What time is it? Well, 6 hours have passed, right? So you look at this guy, oh, mate, it's 5 a.m. Well, you need to get home. And they look at their watch and go, how did you do that, right? That's how it gets done. All right, we'll see you next time.